Welcome to part 2 of artificial neural network. So this is the example we saw in the previous video. So we will work on this. So in this video we are going to deal with the back propagation. As we discussed in the previous video, there are two main steps: back propagation and forward propagation. Sorry, in this video we are going to deal with forward propagation. So let's understand the first hidden layer and input layer, their relationship. So input layer, the number of nodes is total number of independent variables plus one bias term. So for time being, we'll ignore the bias term because we are going to explain you how it works step by step. So now let's look at the first hidden layer. So first hidden layer has got number of nodes, which is equal to it depends on how many number of nodes you want in hidden layer, and that depends on also your algorithm, how your model performs. So based on that, we decide architecture of a neural network, which includes your number of hidden layers and how many nodes you are going to have in each hidden layer. So that depends also on domain and as well as how your model is performing, right? So then you have bias term, so which we add here in every hidden layer, including hidden input layer. But right now we will just ignore that. So steps. So what are the steps? So first what we do is we multiply each variable with respective weights of each node of hidden layer. So what it means is that, see, this input variable, okay, independent variable is connected to this node. So then there is this weight. So it has a corresponding weight for this node. So what we do is we take the value of this independent variable and multiply with this weight, right? And we do it for every node in the next layer and for each node of input layer for all the nodes of the next layer. That's what we do in this. Then we add all the products. So for this node, what we will do is we'll multiply this theta 11 or this weight of this node with this value of this first independent variable. Then we'll take the weight of this, multiply by this value. Then we do the same thing for this and we do the same thing for this, and we add those. So for one node we will have this value into the coefficient plus this value into that respective coefficient, this value plus this value into the respective coefficient plus this value into the respective coefficient, and then that linear equation will be supplied to this node. Then calculate the value based on activation function. So in, for example, sigmoid function is one uh, activation function. So first node of the first hidden, let's look at the example here. So this is the linear equation, right? L11 is the, so this is theta 11 into x1. This is x1, x2, x3, x4. Theta 11 into x1 plus theta 21 into x2. So in this theta, the first digit represents the node number of this input layer, and the second digit represents the node number of the first hidden layer. So theta 11 means the first node of input layer and first node of hidden layer, first hidden layer. So this, now we are just dealing with this hidden layer, this node of this hidden layer. So just focus on this node at the moment. So then theta 11 into x1, then theta 21, because 2 is the second node of this input layer and 1 is the first node of hidden layer, right? So that's why it is theta 21 into x2 plus theta 31, because this is third node, 31 into x3 plus theta 41 into x4, and then we add them together and supply to this. So what is the activation function? Since we have chosen sigmoid, there are other options of activation functions as well. We'll see that later in a later section. So, but right now, just know for this example, we have taken sigmoid function as an activation function. And you know, sigmoid function is 1 by 1 plus e to the power x, right? So x is here, this entire value. So this is what we've done, 1 upon 1 plus e to the power this entire L11, this, and here e is 2.7182818284849. uh, let's look at the input layer and first hidden layer. We continue with that, right? So as we saw, like, we saw this for this node, right? Now we are looking at the second node here in the hidden layer. So what are the calculation? It's similar to like how we did for the first node. So what we do is, again, we multiply each of these values with their respective uh, weight, okay, for corresponding to this node. That's what we have done, right? Theta 1 to x1. So here again, the first digit represents the node number in this, and second digit represents the node number in this, which is 2 here. So you see, second digit is 2 for all the thetas, right? And the first digits are the for the node number of this input layer. So it's 1, 2, 3, and 4, and all these are connected to this node, right? So these are the theta's values, and then again we multiply x1, theta 1 to x1, theta 2 to x2, theta 3 to x3, plus theta 4 to x4. And we just add them, and that's all we do. Again, the activation function is sigmoid, since we are using sigmoid for all this entire hidden layer, and we supply this to this sigmoid function to calculate P12. Again, L12, what does it mean? It means the first is for the your hidden layer, right? This is for the hidden layer, and 2 represents the node number. So here node number is this. So same notation we apply for P also, which is basically probability. So first is the layer number, and this is your node number. So layer number, first hidden layer number 1, and node number 2. So here it is 2. So that's what we are doing here. So likewise we go for all the nodes. Okay, I have not mentioned all the nodes here, just then the last node, sixth node. Okay, so sixth node, again, it's the same thing. L16, 1 is for the first hidden layer, 6 is for the sixth node, right? And again, for each input variable, you have different theta values, right? So first digit is for the first node right here, and second digit is for the sixth node here, right? So theta 16 x1, right? Then theta 26 x2, right? Then theta 36 x3, this one. Then theta 46 x4, this one, right? And we add all of them together, and then again we calculate the activation by using activation function. Sigmoid as our activation function, right? That's what we are doing. So moving on to the next slide. Again, we are continuing with the forward propagation here. Now we look at the first hidden layer and second the hidden layer. See, it's going to be the same. It's a repetitive thing actually what we are doing here. So this is our first hidden layer, and this is our second hidden layer, right? So here we defined our coefficient as beta. In the previous one was theta, here it is beta. Beta 1, 2. The first digit represents the first node number of the first hidden layer, this hidden layer. And the second digit represents the node number of the second hidden layer. That's what it means. This is the convention we are following. So L21 again, now 2 represents here what? It represents your this second hidden layer, right? 1 represents the node number of that second hidden layer. So it's node number 1. So we are dealing with node number 1 right now. So again, it's beta 1 P11, beta 1 P11, beta 21 P12, beta 21 P12, beta 31 P13, beta. So this is what it is, right? So beta 41 P14. So this is this. Beta 51 P15, which is this. Beta 61 P616 is this, and beta 61 is this. So this is what it is. So again, we add all of them, and we calculate the activation function using sigmoid function, right? So again, I've not shown for all the 3 values here, just first node and then the last node. You will do the same thing for this node also, you know. So third node of the second hidden layer, right, which is this. So again, what we are doing is we are taking the respective weight, multiplying with the value, and then adding them together. That's what we are doing. Beta 1 3. 1 represents the digit of the node number of the first hidden layer, so which is this node number 1. and 3 represents the second digit represents the node number of second hidden layer, which is this 3. So this is what we are doing here again. So it's, you can pause and have a look. It's very simple equation. And then activation is again sigmoid function. So we calculate P2. 2, 3 is what again? Just to remind you, P2 stands for the layer number, hidden layer. So it's second hidden layer, right? So that's why it is 2. 3 represents here what? The node number of that hidden layer, which is 3 here. See here, 2 stands for this hidden layer, 1 stands for this node number. So we go on to the next slide, which is again second hidden layer and third hidden layer, right? So this is what it is. There are 3 nodes in the second hidden layer and 2 nodes in the third hidden layer. Here we are using gamma as our coefficient value or weight, or whatever we call it. So again, same logic applied, 3 is third layer, right? Third layer. 1 is the first node. So we are focusing on this node. So gamma 1 is the corresponding weight of this this node with respect to this node, right? So gamma 1 to P21, right? Then gamma 21 P22, right? Gamma 31 P23, this. So all these 3 connected to this node, added together, then activation function 1 upon E plus 1 plus E to the power minus this. Then second node, here second node, same thing, all the connections, right, multiplied by their respective weights, added together, and then we get this activation function. So that's what we are doing. So last is third hidden layer and then output layer, right? So it will be the same thing here, no difference. So here, since it's only one node here, so it's very simple. Alpha is our coefficient value, alpha 11 P21 plus alpha 21 P22, right? This is the linear equation, and this is fed to this node and then applied activation function to calculate activation, right? So now this is the output, right? So this P4 one again, 4 stands for the layer number, which is fourth layer here. 1 stands for the node number. So since there's only one node, so we are getting this P value. This P is basically a probability which will give us the probability of 0, probability of 1 actually, right? Success and failure, that's 1 and 0. So this gives us a probability of 1. If the threshold value, so we can set our threshold value. Ideally it is 0.5. It's less than 0.5. That means it is 0, right? Otherwise, if it is more than equal to or more than 0.5, then it is 1. So this is how our model predicts. Simple as that. So thank you so much. This was for propagation we saw just now. And in the next video, we'll look at the backward propagation. So if you like this video, like, share, and subscribe. Thank you.